This is in continuation of our tutorial series related to kinematics of mechanisms. This is video number 4 out of 10. So we'll be covering GeoGebra in the form of a prismatic joint as well as a revolute joint. Some mathematics related to line and circle. Okay. So before we get into the uh, GeoGebra part, let us try to look into what exactly the mathematical form we are going to deal with. Okay. So if I have if there is a coordinate system, let's say in two-dimensional space xy, and if there is a point p1 and there's another point p2, if I want to draw a segment between them, so that is known as basically it's a segment. How do you do it? So let's say we identify a particular point p that lies between p1 and p2. Now p1 vector is given as small p1 like this. Similarly, p2 vector is given in this manner. This p2 is capital P2 is point, small p2 is the vector, position vector till that point. Now, this particular vector current connecting to the intermediate point P will give it like this. Okay. Now, if I know the value of p1 vector and p2 vector, if that is given, we should be able to locate any point on this line segment. So how do we do it is, so we represent that as parametric equation of a line. Okay. So p vector, this one will be equal to p1 plus this vector addition. P1 vector plus, let's say I'll give it some other name, or I'll write p1 p vector till here. Now how do I get this particular term? So I introduce a parameter called t, which is a scalar, into delta p vector. Okay. Now what is delta p vector? Delta p vector is p2 vector minus p1 vector. This whole thing here, this is delta p vector. Okay. So what it means is, for t is equal to 0, if I put the value of t equal to 0, what do we get? P point will be p1 plus 0 into p2 minus p1. Okay. Now 0 scalar multiplying a vector, it will become 0. So point p will be equal to p1. That means if t equal to 0 will be at this particular point. For t is equal to 1. Okay. So we'll still write the same equation. Vector p is equal to p1 plus p1 plus the t value is 1. 1 into delta p vector is p2 minus p1. So this p1 will get cancelled, so it will become p2. That means when we come till here, t is equal to 1. So when we range t between 0 and 1, we get line segment. Okay. So typically in GeoGebra, it is very easy to create a line segment. But if you are using, let's say, some other uh, form of programming, then this representation is very useful to draw a line between two points. Similarly, we'll also look at parametric equation of a circle. So if I'm here and if a radius is given to us, if I want to move on this circle, let's say I have a point P. So the radius does not change of a given circle, it is R. The angle theta has to be measured with respect to the positive x-axis. Theta is counterclockwise from positive x-axis. Okay, so if I vary the value of theta from 0, goes around till 360 degrees or 2 pi, I'll be tracing this circle. So the parametric equation of circle is given as P is equal to, along x direction, this guy is r cos theta. I think in one of our earlier videos we have done this. Similarly, along y direction, Py will be r sin theta. So the parametric equation of a circle is given in this manner. Okay, now what will happen if we try to take slightly different circle? Let's say I have a circle which is centered at C, and basically it is still having some radius, and that radius, let's say, is given in this manner. What is this point P? How do we represent that? So obviously we'll consider the same situation. Theta is changing with respect to the horizontal counterclockwise, and this distance is, let's say, given by the center of the point C, and similarly along y direction it is Cy. So now parametric equation of a circle will be Cx plus r cos theta. Cx plus r cos theta, and similarly for y direction it will be Cy, this is Cy plus r sin theta. Cy plus r sin theta. So this is the generic case. So we are now going to try to reproduce this in GeoGebra, so that we'll be able to understand it better, and later on we'll see that whenever we have a slider, so this corresponds to a slider in theory of machine. Slider crank and other mechanisms will have a slider that translates, and what we have done here, this corresponds to a revolute joint. In other way, this is a revolute joint, and here it is slider, or we can also call it as prismatic joint. So in general kinematics that we study, we'll be dealing with revolute joint and prismatic joint a lot. So it is good to know how those joints behave in real life situation. Okay, let me open up GeoGebra geometry. Okay, first things first, we'll try to have access, okay, and show grid. Now we have already learned a bit of coding in one of the other videos. I'll start off directly. Capital O is equal to 0, 0. So that's point O. Now I want to have the same situation, P1 vector, P2 vector, and a point moving down. So P1 capital is, let's say I'll write 2, 4. P2 is equal to, let's say 6, 1. Okay, so those two are similar to our diagram. Now I want to represent parameter t. T is equal to 0. Okay, later we'll put a slider. T changes from, if I go to settings, I can have 0 to 1. So the value of t will go from 0 to 1. Now what else do we need? We'll require a small px is equal to x coordinate is going to be okay. So one more thing what we can think of is, in this code we have directly given 2 4 and 6 1. If I want to retrieve that information, I can also do it in this manner. Okay, p1x is equal to x of p1 in this manner. Okay. Similarly, p1y is equal to y small y of p1. Similarly, we'll have p2x is equal to x of capital P2, p2y is equal to y of capital P2. Okay. So now we want to create that vector as I mentioned. So px is equal to p1x plus t is a scalar into p2x minus p1x. See, we are trying to do this component by component. Vector wise also we can do, or x component separate, y component separate. Okay, so I have introduced t. Right now the value is 0. Okay, this is how we'll get px. Similarly, py is equal to p1y plus t into p2y minus p1y. This is py. So how do we get point? P is equal to px comma py. There is a point p here. Now when I move this t1, you can see that as the value of t is changing, the point p will go from p1 to p2. Okay, very simple. So it's just that we should understand the concept. As t changes, it will move from here till there. Now you may be wondering what happens if the value of t, this parameter t, is less than okay. So let me try -2 till, let's say, +3. So what will happen is it goes before point p1, and as the point, the parameter becomes more than 1, it goes beyond also. So if you put it -infinity to +infinity, it will have line in both the direction. Okay, so this is about parametric equation of a line which is equivalent to a prismatic joint or a slider. Right, now let me try to clear all, start. We will do the parametric equation of circle. I have done it earlier, but still this is okay. O is equal to 0 comma 0. What are the equation we'll require? We'll require radius. Let me give radius as 4. We'll also have theta, let's say 0, px. Okay, I'm going to give a generic case. The generic case is what we did here, this one, cx cy. So we'll have cx is equal to 2, cy is equal to 3, then capital C is equal to cx comma cy. Now we need to have a point moving on a circle with radius 4. So for that we'll require px is equal to, again component by component I'm doing, cx plus r into cos of theta. Py is equal to cy plus r into sine of theta. Capital P is equal to, sorry, capital P is equal to px comma py. Okay. Now theta, let us put a slider, create slider, and settings I can change. Please note that theta is in radians. So we want to go from 0 into 2 pi, 2 into pi. If I click on this play button, you can see that the point P is moving on a circle, and this is typically the case of a Revolute joint. So imagine there's a, let me try to put it this way. I can go to the tools. I'll just create as, so imagine this is one of the link. This is another link. And if I move the theta value, it will behave as if that I have one link and the second link is rotating with respect to this revolute joint. So that is why we wanted to have this parametric equation of circle. So in the next video, we'll be also looking at what are different mechanisms, and there is something known as degree of freedom using Grubler's-Kurzbach equation. Similar to the earlier degree of freedom we have already done. Degree of freedom of a point, degree of freedom of rigid body, degree of freedom of kinematic pairs. Now we'll be looking at a mechanism and how do you find degree of freedom. Later we'll also look at few sample problems on planar and spatial mechanisms. How do we find degrees of freedom? Later on we'll look at different planar standard mechanisms, 4-bar slider crank double slider, followed by GeoGebra simulation of those mechanisms. Then we'll have a quick overview of MechAnalyzer software. And finally, we'll try to take one sample mechanism found, let's say, on the internet, and how do we analyze that. Thank you very much.